Hello and welcome to my channel. Today we want to practice object-oriented programming with a small coding challenge. In this video we are going to solve a coding challenge initially and then refine our solution towards a more object-oriented code. Our focus here will lay on improving encapsulation and conforming to the tell, don't ask principle. If you never heard of this principle before, don't worry, we will cover this later. The coding challenge is as follows. There is an expedition of elves, each carrying supplies. The goal is to find the one elf carrying the most calories and print out the amount of calories carried by this particular elf. To gather all calories, each elf writes what he carries on a list, resulting in the following. Each block says what calories the elf is carrying. A new line separates the elves from each other. To implement a solution, we will need to read in text in some format and find the block which is, when summed up, the max amount. We start by simply reading in from the command line. Later we will change this to read in a particular text file. For doing this we use standard Java tooling, the buffered reader with an input stream from the system input. To store the max amount of calories found so far, we use a variable called max calories. The variable current elf calories stores the sum of calories carried by the elf that is processed currently. We will process the input line by line. If the line is empty, we know we have a new elf. If the amount of calories that was calculated in the last block is bigger than what we currently know are the maximum calories found so far, we can update the max calories variable to the new value. And as a new line indicates a new block is coming, we reset the current elf calories variable. If the current line is not empty, we need to add the value from that line to our current elf calories variable, effectively summing up a single block. When all the lines are processed, we can simply print out the value stored in the max calories variable. After saving, we can run our application. As we are only reading the input from the command line, we simply enter the calories. One of the first changes we will do in a moment will be to read in the text from a file instead. Okay, wait a moment. So our application is up and running, solving the problem from the coding challenge. Are we done yet? No, certainly not. The code is awful and coding challenges are here to help you improve as software developers. If we were to develop in a purely procedural style, the solution maybe would be sufficient. But imagine we need to add features to this code. The app class would grow and all the conditional logic that is already in place would become harder to understand and harder to maintain with each enhancement we are adding. Breaking up the app class would certainly be a good thing to maintain good code quality and be able to add features later without bigger issues. And as mentioned before, we want to read in a text file rather than the system input. For simplicity, we already have placed the text file in the source main resources folder. To read in from this location is fairly easy, as the file is already on the class path. Luckily, the buffered reader is flexible enough to take input from another input stream, so we just need to replace the system in with the updated input stream from our class loader. A quick test will show if the file is read incorrectly. Here is the text file we just processed. As we see, the format is exactly the same as we previously typed in manually on the command line. For our next refactoring, we need to identify some stuff that can be extracted. And secondly, where to put this stuff. As we want to code closely to the problem domain, at least two new classes of objects can be identified, an elf class and an expedition class. The elf class will be responsible for managing the calories, and the expedition class will collectively maintain all the elves. What our app class will need to do is translating the text file to our domain objects, the elves and the expedition. The determination of the elf carrying the most calories will be done by the expedition class. This frees the app class from these two responsibilities. So the first thing we do is create a new class for our elves. Each elf carries some amount of calories, and we need to be able to update this value and to retrieve the amount of calories. Our app class now needs to construct an elf for each new block it encounters during processing, more concretely whenever it hits an empty line. Second, we create the class for the expedition. Side note: to increase encapsulation, I stripped down the visibility of my classes to package private. This is not mandatory but will help in later development, as we need to carefully think about our dependencies. Public classes are much harder to maintain because they easily attract dependencies, and once they are public, it is very hard to narrow the visibility. The expedition class will collect all our elves. Besides, there will always be a current elf, so our expedition class will be stateful. Naturally, we need to add new elves to our expedition. The last elf added is our current elf, the one we can add calories to before proceeding with the next one. Clients will be able to retrieve all elves in a collection. To avoid them messing with this collection, we will give them a copy of our list. This way, clients won't be able to accidentally edit the expedition's collection of elves. Now we will add functionality to add calories to the current elf. The expedition will, in this case, simply delegate to current elf. The next step is to update our app class again. It will be responsible for creating an expedition object and adding elves and calories to it. To determine the max amount of calories, we simply use a functional approach to process and compare all the elves from a collection using Java's streaming API. For this, we simply map each elf to its calories and determine the maximum value. A short test verifies we did not break our small program and the objects working correctly. Are we done yet? For sure, we improved the app class, but our solution is far from object-oriented code. Don't let the code fool you. Just because we introduced objects doesn't mean we introduced good objects. Good objects have numerous traits, one of them being encapsulation. Do you see where encapsulation is violated in the expedition and the elf class? Objects should have strong encapsulation barriers. And of course, one could argue that we are doing this by setting the attributes of our classes to private. But this is not true. The mere act of exposing the internal attributes with accessor methods to the world breaks encapsulation of our objects. Why? Because sooner or later, more clients will start to depend on the internal structure of our objects, as the app class already does by retrieving the calories from an elf. And the more clients do this, the harder it will get to change this. This defeats the purpose of encapsulation, because now our objects cannot freely adapt to changing requirements anymore. By truly making an object's internals private, we can make sure no one will depend on it. Maybe you see a connected issue here. Ever heard of the tell don't ask principle? It is closely related to this issue, because when clients start to ask an object about data and then doing stuff with it, you certainly have procedural logic in place. So our next goal will be to truly encapsulate an elf's internals. This will force us to really think in terms of objects, rather than procedural if this then that logic. To make things clear for us, we will completely delete the accessor method from the elf class. Next, we need to inspect the now broken code and need to understand what the client wanted to accomplish with the data. In this case, it determined the maximum value. This is logical. To determine the maximum value from a set of values, the client needs access to these values. By removing this option, we need to find another mechanism. Here, creativity is needed, but this way we move to a more object-oriented solution. In this case, we choose a simple solution, making the elves comparable to each other by implementing the comparable interface. This way, no outsider needs access to the calories. The compare method seems a little antiquated, since we only need to return integer for the comparison result. Positive if the compared object is smaller, negative if the compared object is bigger, and 0 if both objects are the same. To determine the maximum value, the expedition class now only needs to compare all the elves with each other. To move to a tell solution, we will tell the expedition class to report the maximum value to some print stream. Here the comparison of our elves actually will take place. We use an iterator to iterate through all the elves. Responsibility of the expedition class is only to determine the elf carrying the most calories. As the calories of an elf are behind strong encapsulation barriers, we need to move to a tell solution here as well. We achieve this by telling that elf to report his calories to the print stream given to the expedition. Finally, we can free the app class from the logic of determining and printing the max calories as well, as we distributed that between our expedition and elf class. This is all for today. As always, we could improve our solution further, but we made a big step towards object orientation by distributing behavior away from the app class and encapsulating the elf and the expedition state. If you liked the video, hit the like button and subscribe to my channel. See you soon!